Okay, so we'll continue from here, and as I said, we'll try to run through this a little quickly, and you can stop and ask questions if you need to. Okay. So in general, in dealing with binary images, doing operations using logical operations is much better, especially because we are dealing with zeros and ones, and performing logical operations on binary images, one, makes the processing a lot faster, and also the number of operations that we typically would like to do in terms of being able to process those kind of binary images is relatively limited. Okay, and we'll talk a little bit about what kind of operations are meaningful to do on binary images. So first of all, I mean, generally when we obtain these binary images, they can come in a variety of forms, right? If you look at images like these, they have a whole bunch of regions in them. All of them are binary. You can have regions with big holes, small holes, just odd kind of shapes that may form because of your thresholding operation, right? Most of the time you're dealing with binary images as a byproduct of a thresholding operation. Sometimes you're working with images that directly are coded as binary images, like the one we saw, you know, as an example, if you were writing on a tablet or something like that, would be a direct binary output. But in most cases, it's a byproduct of a thresholding operation. In some cases, you're dealing with sort of images which are binary, but the context that's present within that may not necessarily be regional, it may be contour based, right? So you may have single pixels that describe the content of an image, right? So in this case, imagine all of these letters and each pixel in there is just one pixel, right? The thickness of each line is just one pixel thick. You may have images like that. So in general, whenever we talk about binary images, they're dominated by two types of images, regions or contours. Right? And we have to work with both of those to process those images to extract more information off of it. Now, whenever we look at binary images, and in general for all digital images, the fundamental thing that you're always working with is the pixel. Right? So even though we see images that have these kind of shapes, right? For example, one can look at this image and say, yeah, I mean that's a circular object, but when we look at it at a pixel level information, right, we are going to be limited by the square or rectangular resolution that a pixel presents. Right? So it's not going to be smooth and continuous, it's going to look something like that. Now, as a result, all the processing that we do on these images have to be defined in terms of pixel level operations. Right? And that's exactly what we do for binary images. So the fundamental operations that we will work with in terms of binary processing, again restricting ourselves to logical operations, are going to be simple things like logical NOT, right, which is basically complement of the image that you're working with. We can work with a logical AND, which can take two images and AND them together, and everyone knows what a truth table would look like for an AND operation, right, especially in the context where we're only dealing with ones and zeros, right. So you have two images for which each pixel is, let's say, 0, then the resultant of an AND operation is also going to be 0, right. If both the pixels in the two images are 1, the resultant is going to be 1, otherwise your result is a 0, right. So we can extend these kind of operations on n number of images, right. We don't have to restrict ourselves to 2 images, it can be any number of images that we choose to work with. Same thing applies for a OR operation, right. We can perform OR operations on images, binary images as well, right. And the resultant is going to be based on the truth table for a OR operation. Same thing applies for OR, which is we can apply that for multiple images, right. Now, in general, we can look through all possible Boolean algebra operations as long as we have a Boolean algebraic operation that we would like to perform. We can certainly do that on a binary image or a multiple binary images that you're working with, right. So you can actually simplify almost any kind of operation that you want to do on an image based on basic laws of Boolean algebra, right. So when you're dealing with multiple images, 3 images for example, or n number of images, and you try to perform a AND operation, yeah, well, you can actually simplify that operation based on associative laws, commutative laws, distributive laws, as well as the De Morgan's law. Right? So all of these laws are important for us to remember because it helps us simplify the operations we wish to perform on an image. Right? Now, there is one other operation besides AND, OR, and NOT that we care for in terms of our library of binary image processing operations that we like to maintain, and that's the binary majority. Right? Now, always keep in mind that whenever you try to apply a binary majority, it has to be applied on odd number of variables. Right? Obviously, we can't choose a majority if you have even number of variables that you're working with. Right? So if I have, let's say, 3 images that I'm trying to compute the binary majority over, well, basically the output is going to be the maximum number of zeros or ones in those 3 images that you're working with. Okay, so that would be the simple truth table for a binary majority operation. Now, this operation is actually very useful, and you will see how that allows us to actually design a filter around this operation. Right? Now, if you were to think of this binary majority operator and say, well, if I wasn't dealing with a simple binary image, if you were working with a grayscale image, what would your majority operator sort of translate to? What would be the equivalent of a majority operator if you weren't limited to binary images? Sorry? No, keep in mind that you're performing all of these at a pixel level basis, right? So you have a set of 3 pixels, right? And instead of 1, 1, 1, let's say they have a grayscale value, right? So it's an 8-bit value. Sorry? Mode. Yes, close. Right? What other things can you, well, what would be another equivalent of a mode? Median. Not the higher value. Okay? What we are computing here is not whether the value is high or not. We are computing the majority value. Right? So it's the majority number of values that are consistent. Right? So we're not computing max or min. Right? That's different. But we are computing majority. And the equivalent of that for a binary, or sorry, a grayscale image would be a median operation. Okay. If all 3 were different, well, so of course it can never happen in a binary image. In a grayscale image, the equivalent of a majority is a median operation. Right. So you would pick the median of the 3 values. Okay. And we will see why this operation is useful in terms of a filtering property. Okay. Okay. Of course, same thing translates. We can apply majority to n number of values, n number of images, whatever that might be. Now, keep in mind that whenever we talk about Boolean operations, in terms of our image processing operation set, most of the times you're not going to need anything besides NOT, AND, and OR. Okay? We typically don't try to use other operations from our Boolean algebra set. Yes, besides these 3, we will use majority as an operation because that has a unique property. Okay? Now, these 3 should suffice for every binary operation we need to do. More importantly, we restrict ourselves to these 3 because these 3 are, why would we restrict ourselves? Sorry? Well, yes. So all the other possible operations can be broken down, can be simplified into operations based on these 3. But is there any reason for us to simplify that? If I gave you basically an operation to perform which involved other operations besides these 3, why would you simplify it so that you can break it down into a combination of NOT, AND, and OR? Why would you rather not just apply what I told you to? Very good. Because your arithmetic and, well, basically your logical unit on your processor essentially has these 3 wired in, right? These are the most optimal performing operations that you can do in terms of logical operations. Everything else are basically combinations of these, right? So your logical unit has to perform the translation in order to simplify the operation you're trying to perform. So rather than you wasting the time of the CPU to do that, well, you want yourself to simplify it before you actually code it, okay? All right, now let's look at very simple things as to what you can do with these operations, right? A simple NOT operation, right? The way we would define it is if I do a NOT on an image, right, I get a new image which is given by J if the original image is I, and basically that operation is an inverse, a NOT of every pixel in the original image, okay? And the end product is nothing but a binary negative of your input image, okay? So if you remember the images we saw earlier, basically these are exact binary negatives of what was there before. So that's the simplest operation you can perform. Now if I were to do a binary AND, well, the end result of that is if I take these two images, I1 and I2, and define an AND operation of I1 and I2 to just get a new image J sub 2, then all I get is the overlapping black regions that are present between the two images, right? So the product would look like that. Okay? Now if I took a OR operation, right, I would get an overlap of the black regions that are present in the two images, and I would get a resultant image which looks like that. Okay. Now in general, doing basic NOT and an OR operation on the global image is not very useful. Okay. I mean, you kind of saw what it does. Basically gives you either a binary negative, gives you an overlapping region of blacks or objects that you have, or gives you the gives you everything, that all the regions that are present, all the black regions that are present, okay? But doing them in general for any processing purposes is not that useful. There are a few cases where that might not be true, and a simple example would be in a machine inspection type of setting, okay? And keep in mind this would be a rather constrained setting, but imagine a scenario where you were to design an assembly line inspection system, and the assembly line, the only thing it was producing was nuts, okay? So if you had basically a specification of the particular part that had to be produced, and you had an image of it, now you have a camera essentially pointing to a conveyor system where these nuts are being manufactured, and the job of this particular vision system was to figure out if any of these parts were defective or not. Okay? If this was the application we were designing, then what you have is essentially a stored model of what that part should look like. You have the camera which is going to acquire an image of every part that's placed on the conveyor belt, and you basically have a processing unit whose job is to figure out how different this acquired image is from the specifications that you have at hand as to what this part should look like. Okay? So this is a simple application of binary image processing where, let's say you have a mechanism to convert each of these images into a grayscale image, into a binary image, right? This is what it looked like, and now you have to compare it to this particular binary image. So you have two images that you have to compare with, right? Let's call this I model, and let's call this just I, right, for the image that's acquired. So what would be your solution? How would you actually go about doing this? Yeah, right. So you can basically do a exclusive OR operation, right? An XOR operation would essentially give you what is the amount of displacement that's present or difference that's present between the acquired image and your model. Okay. Now, would I actually just implement an XOR, or would you simplify it and implement something different? Keep in mind that, so what's an XOR in terms of NOT, AND, and OR? Okay. So what you would have to do is basically take the knot of the model, right, and end that with the image. You also take knot of the image and you end that with the model, and you take a OR of the result of the end operations. Now that's equivalent to the XOR of the image and the model. Okay, so you would actually want to simplify your operation into these operations, which are nothing but ANDs, NOTs, and ORs, in order to compute your exclusive OR. Right? That would give you essentially your displacement, which is this. Okay, so this is what it would look like. Right? If I have a model that I'm trying to compare against an image that I acquire, this is the result of the exclusive OR. Now, of course, once I get this, I need to do something more in order to figure out whether I'm going to accept this particular part or not. Okay? Well, and that's dependent on the specifications that you're given within which the vision system needs to work. So one simple thing you can do is you compute the percentage of black pixels that you get as a product of your exclusive OR operation and take a ratio of that number of pixels to the size of the object. Okay? So if I get that and say if this percentage is higher than a certain threshold value, well, I need to reject that part. If not, okay, I'm happy. Right? Make sense? A very simple processing pipeline, but can be effective in an application which is constrained and would look something like that. Now, in this particular example, basically all you've done is performed global binary operations. Right? You perform those operations on the entire image, and they gave you something useful as an end result. Right? These kind of applications are limited. Most of the times, we perform these kind of binary operations within local regions of an image, and they have a different benefit. We'll look at that. Okay? Now, one of the other operations that's very useful to do in terms of binary image processing is something called blob coloring. Okay? Blob, well, besides the sort of the common meaning that you might use in a English language for blob just being as an object, blob also stands for binary labeled object in terms of image processing. Okay? So just given the definition of blob, the intent of doing blob coloring is to look at the black objects or binary objects that are present in an image and essentially label each one of them or count each one of them. Okay? Now the distinguished or distinct counting of each of the object can help in some of the processing that you may wish to do. For example, if you're given an image like this, and you are told that, well, find me the largest object that's present in this image, how would you go about doing it? Sorry? Very good. Counting the pixels, right? So counting the pixels for each object. Now, how do you know that there are a common set of pixels that actually belong to a single object? How would I know that? Very good. So same question again. How do I identify the different objects that are there? What makes each of these objects an object? Besides you looking at it and telling me that's an object, in terms of... Sorry?
A group of connected pixels together make an object.
Yes, very good. So group of connected pixels together make an object. Perfect definition. How do I find the group of connected pixels?
By background.
Sorry?
By the background.
Well, by the background, can you elaborate?
Like the boundary of the particular group of pixels, we can identify that this is a group, and the difference between the...
Again, how do you find the boundary? Difference in the pixel color. Well, all these pixels basically have black color, and everything else in the background is white. So how do I find the boundary? Sorry?
Same gray level of the object.
Well, all of these objects have the same gray level, right? But there are 1, 2, 3, 4, 5 distinct objects in this image.
Now there is a specific change in gray level value at the edge of the...
Okay, so you're getting closer. So you're telling me that basically you want to look for the presence of a 1 next to a 0, right? And this is a binary image, right? These are not gray level images, keep in mind. This is thresholded. Uh-huh. Right. So you're still sort of on the notion of finding a contour, right? I still have to find a contour somehow. How do I get a contour? So according to your definition, right, which is a significant change, basically you're going to tell me that if I'm raster scanning, this is the boundary pixel, this is a boundary pixel, this is a boundary pixel, this is a boundary pixel, right? Which means along this line there are 1, 2, 3, 4 objects. Uh-huh. Right, and how do I know there's a connectivity? All right, there are only 2 colors here, 0 and 1, right? So how do you, what is a different color? Okay. Okay, very good. Okay, so I'm looking for a black pixel which is all white around it, right? That gives me a single object, but that's 1 pixel object, right? I don't have any of those in here, right? So this is, you know, I mean, visually it's a very simple problem, right? You can look at it and tell me there are 5 objects. Okay, in terms of processing, it's not that straightforward. Okay, and in order to actually do this counting, there are the algorithm to do it is called blob coloring. Okay? And there are probably a dozen different approaches to doing blob coloring. So there are a dozen different algorithms by which you can actually solve this problem. It's not a close-ended solution. And in fact, you can go back in literature and probably, you know, at least 6 years back, there was also still a paper that was published on coloring, keeping in mind that blob coloring was probably something that we started working on about 50 years ago, right, as the first step in image processing. So, you know, all right, so one of the ways that we can look at this in terms of an algorithm is to define something very simple, okay? So here's what we normally do. For a binary image, right, we treat this as a coloring problem where we want to assign a new color, right, as opposed to zeros and 1. We want to assign a new color, a new label to each object that's present in the image. Okay? So what we can do first is create an array of colors, if you will, and set them all to 0, right? The array of colors that we will create is basically a region counter, and we'll call it R. Okay? And we'll set that to 0. Now we can start. Keep in mind your image processing in almost all cases is based on a raster scanning operation. Okay? We start from the upper top left corner of an image, and you're going to scan 1 row at a time, okay? And you're going to scan through the entire image in order to perform some operation till you get to the lower right corner of the image, at which point you're finished processing the image, okay? Do you remember, I think we had basically, we had defined an operation where essentially we were going to perform something which was for each row, for each column, right? Yeah. So any operation that I define over here within this loop is going to be something that I process in a raster scanning fashion. All right. So imagine a raster scanning where you start and you say, I come to the first pixel in my image and I check if it's a 1, right? Because I need to check for presence of an object, right? If it's 0, it's background, I don't care about it. But if it's 1, then I need to check for its neighbors, right? And the neighboring condition I want to check is the pixel above it and the pixel to the left of it, right? The reason we restrict ourselves to only those 2 pixels is because in a raster scanning fashion, those are the only 2 pixels you would have visited before getting to this pixel, right? Everything else is going to still come. You're not visited those pixels as yet. Agreed? So this is the first condition we check for. If this condition is present, then we know that this is the beginning of a particular object, region. Okay, and we would assign this essentially a region color saying k. Okay, at that point we would increment the counter of k and set that to be k plus 1. Now you would actually not only check for this condition, but you want to check for multiple conditions at that point. The other condition you want to check for is this, right? Which is if I come to this particular pixel, it's possible that actually this is a neighbor of a pixel for which I've already assigned a color, right? And the only two pixels again I would have visited would be this and this, right? Which means if this is a pixel that I visited before and already assigned it a color, then this is a continuation of that region and I want that color to be the same as this. Agreed? So that's exactly what you will do. You will set this guy's color to be the color of this guy. Okay? You don't increment the color counter at that point.
What do we do when we are on the first pixel? Because we don't have anything above it or before it.
Very good. So basically, I'll talk about what you do with boundary pixels in a second, right? So for now, imagine that you're running your, okay? So this would be actually all right. So imagine that we are discounting the boundary pixels in an image for now. Okay. All right. What's the other condition? We have to check for that kind of condition to happen, right? And again, in that case, we know that the pixel that is basically the corresponding pixel here, that's a connected pixel. And the final condition would be this, which is this is connected to both of these. Okay. Now it's possible that, in that condition, of course, it's simple, right? You're going to set the color of the pixel corresponding to its previous neighbor. But in this condition, this is a special case, right? Because it's possible that you assign this guy a color and you assign this guy a color. And these two are actually going to be different colors, right? Does that make sense? Because when you got to this pixel, right, all you checked for was this pixel and this pixel, right? And both of those were white, so I assigned this guy a new color. So when you check for this condition, if this condition is valid, then you have to actually reassign the colors for this pixel as well as this pixel to be the same as this guy. Make sense? Yeah, everyone okay with that? Okay, so once you do that, then okay, you basically perform this operation for the entire image, and the end product of that is going to be essentially a array that you get, which is R, right, which has a color value, a k value if you will, for every pixel in the image. Okay. Now keep in mind that that k value doesn't have to be in order. Okay, which means if you have 5 objects, you're not going to end up with k equal to 1, 2, 3, 4, and 5. Okay, because you are reassigning the k values as you scan along your image. But what you will find is that there are going to be a k value that is built up. So think of your array as a counter, a bin, okay, and you're putting the number of pixels in each bin. Okay, all you do is go visit your R array and see how many pixels are sitting in each bin. Okay, that should give you the number of objects you have. More importantly, it should also give you the number of pixels for each object or each region that you have in the image. Yes? All right. So this would be a simple blob coloring operation, and an example output for something like that would be this, right? 1, 2, 3, 4, 5. You would have 5 regions, and these would be the corresponding number of pixels that are present in each region. Okay. Furthermore, because you know the number of pixels, you can actually go back and see which has the highest number of pixels and say which color object is the largest object that you have in the image. Okay. Now, what would be the use of doing blob coloring. What do we do with this? Counting objects, right? The other thing is filtering, right? Getting rid of small objects, right? For example, in this case, if I say, well, all I'm interested in is the largest object, because given your application, you may know a priori that you only have one object in an image, but because of your thresholding, you may get erroneous objects in the image that you actually want to get rid of, right? So by doing blob coloring and finding the largest, you may be able to get rid of everything else. Okay? So you set all the other pixels to 0 and you're left with only one object, right? So one application of doing blob coloring would be minor region removal. Now, if I have the result of this, which gives me this object, right? But this object, again, because of thresholding operation, is not perfect, right? It's got holes in it. How would I fix them? Very good. I can do same thing, but yeah. So I can do something very simple. I can take the inverse of this image, right, and then do blob coloring, right? If I take the inverse of this image, what I get is huge black region. I get small white regions, right? And wherever I have the object, that becomes my background, right? So if I do the inverse, do blob coloring, get rid of all the small ones and take an inverse again, I get a, right? So I can do that as well, which is a filtering operation as a byproduct of blob coloring, right? So I can do that, find out the largest, the colored blob, largest one would be the background, again do minor region removal, take the complement, and I get the full object. Okay. So another application of doing simple blob coloring. Okay. So we can do this and get a whole object. Right. Obviously, doing this is not going to solve all problems, but it's a processing tool that we can use, an algorithm that can be used depending on the application, right? Now, what are the other problems, potential problems they can imagine in binary image processing, right? Well, imagine a scenario where this object, right, that you're getting is a byproduct of thresholding operation, which is imperfect, right? Because we all understand the kind of histogram variations that exist in images, and there are no perfect solutions to doing thresholding, automated thresholding, right? So it's going to be variable. Now, it's possible that what this object was actually a filled contour, right? Was a closed object, and portion of this is missing. Right? Blob coloring is not going to fix that, right? We're not going to get a solution out of blob coloring to do that. Furthermore, we're not going to get a solution out of and or not any operation that we have seen so far in order to complete that missing region. Okay? So, what can we do? Sorry. So, in order to deal with shapes, right, binary shapes, we introduce a class of operations within the context of binary morphological operations, right? Morphology and basically meaning shape, right? We're trying to modify the shape of binary images by performing a certain set of operations. Again, they are binary operations, Boolean operations, but somehow they affect the shape of the object in different ways, and we have to see what might be useful for us. So the basic operations under morphological operations we care for are operations such as expand or dilate objects, right? I may have an object that I want to make larger, right? So dilation of the object. Okay? Erosion of an object, making it smaller, shrink the object somehow, right? We may be interested in smoothing the object boundaries, right? So some kind of a smoothing operation, if you will, a filtering operation, in order to maybe get rid of small regions or holes that are present in the object. Okay? Or we may be interested in performing operations which fill gaps potentially in the object that might have come up, or fill peninsulas. For example, if we go back over here, right, essentially looking at an object which has a gap in it. Right? If we need to fill that gap, how do we do it? Right? We need to look at morphological operations in order to fill those kind of gaps. Okay? So before we can talk about morphological operations, we need to understand a little bit about how we can construct these kind of processing algorithms on it. So the um, fundamental structure within which all of these processing can be performed is under windowed operations. Okay. So first we have to think of creating geometric relationships to the number of pixels that we are interested in processing. Right? If you looked at global operations, all morphological operations fall under the notion of local operations. Okay? Which means in order to define something local, we need to define the number of pixels on which we would perform an operation. Okay? And the number of pixels that we perform the operation on is given by a structuring element that can be of different size and so on. Okay? So if you think of structuring elements for now, windows, these are all potential windows. Each one of them has a different size and a different shape. Okay? So what is the use of these kind of structuring elements? Well, first and foremost, every structuring element defines a geometric relationship to the window. So if you have a large window over which the structuring element is placed, the pixels that you actually operate on are going to be the ones that are within this element alone. Right? So if I take, let's say, an image, okay, that's about that size, and I have the structuring element that I place on it, right? And let's say I want to perform an OR operation. Okay? The OR operation that I perform is going to be limited to the number of pixels that are overlapping within this element that I've put on the image and nothing else, which means my OR operation does not account for the pixels that are out here. Okay? Only within the structuring element is what I will use in order to perform an operation. Okay? So that's the basic purpose of a structuring element. Now this is fundamental in image processing in the sense it is not restricted to doing binary operations. In fact, we will see that all grayscale operations will also be performed using windowed operations. Okay? Now, structuring elements can be row structuring elements, can be column structuring elements as well. So they don't have to be two-dimensional in shape, they can be one-dimensional as well. Now, in general, any structuring element that we use has to be moved across the entire image in order for us to perform that operation on the entire image. Okay? The movement of the structuring element is a pixel by pixel movement, independent of the size of the structuring element. Okay? That's the only way we can affect every pixel in our image by that particular operation. Okay? All right. Now, all structuring elements that we construct, we tend to make them symmetric, okay, so that whatever operation we perform on the image is symmetric over the image and is independent of the shape of the object, right? For example, if I want to perform a particular operation on an object, and if the object is rotated somehow, then the particular effect of the structuring element is minimized on the shape of the object, right, if the window is symmetric. Furthermore, we try to also, well, not try, the constraint on all structuring elements is that they have to be odd numbered. Okay? The number of pixels enclosed within the structuring element has to be odd numbered. They can never be even numbered. Okay? For simple reasons of, as an example, if you had to perform a majority operation on a structuring element, if you didn't have odd number of values, how would you actually perform a majority? Okay? So this would be an example. If I took a structuring element like that, that's defined in blue, right? And if I were to actually apply that on the image that's in the background, well, the way I would have to do it is actually move that window by raster scanning it across the entire image, right? So I would move it one pixel at a time, raster scan it across the entire image till I came to the end of the image. Okay? Now, as I said, this is the same operation you perform on gray level images as well in terms of the structuring element. So there is commonality of what we are defining here. As a result, we will also try to define this in a little more concrete fashion. Now, keep in mind that inherently the windowing operation is a sequential operation, right? You're doing one pixel at a time across the entire image. If you wanted to do this in a parallel fashion, certainly feasible, right? The only thing is you would have to define windows enough to cover the entire image and run them in parallel. Okay? Now, the end product would be identical under parallel operation or sequential operation. The reason for which is because any pixel that is affected by the windowing element is not considered in the next sequential step of the processing. Okay? Which means, let's say that I'm working on a 3x3 set of pixels. Okay? Now, given my image, okay, I'm going to move this window over one pixel, right? So during the next step, the 3x3 will be sitting here, right? But when I do this, any pixel that got affected in this region is not something I will consider in my next step, right? I will consider only the original value of the pixel that's present in the image. That's the reason I say that these would give you identical results, whether it's parallel or sequential implementation. All right, so let's look at some of the basic windows, right? This would be a row 3 window, this would be a row 5, column 3, column 5, right? And generally we will define all windows based on the shape and essentially the number of elements that are present in each windowed shape. Okay? So, and you will always have a +1 because it's going to be odd valued. Okay, so we'll define it to be 2m plus 1. M is something that we will formally define in a second. All right. Nope. All right, these would be simple examples of two-dimensional images, two-dimensional windows. Okay, a square, cross, square with 25 values in it, pixels in it, circular with 13, cross with 9, and again these would be defined based on the shape and the basic elements that are present within that. Okay. Again, these are most common window shapes. You don't have to restrict yourselves to these shapes, right? You can come up with your own symmetric shape, and that's absolutely fine. Keep in mind that the result of using any of these structuring elements is different. Okay? So if I were to perform an OR operation using this kind of element versus this, the product result is going to be different. Okay? It's not the same. So each element produces a different result, all of which are valid. Right? There's nothing like an invalid result. All right. So let's define some basic notation so we can use them. We'll define first of all any window that we create, any structuring element with the letter B. Okay. Now, the window is nothing but a mechanism for collecting local intensity values that are present in the image, which means we can define the coordinates of that window essentially as shifts. Okay. So we'll define this window B sub I being equal to a collection of coordinate values defined by m sub I, n sub I. Okay. All of these are going to be centered around 0, 0. Okay. So in constructing any window, you will always define the center pixel to be 0, 0. Okay. Right. Every other position in the window is a coordinate shift from 0, 0. Right. For example, this would be -1, -1. This would be 1, 1. Yeah, make sense? Okay. Which means we can define B as being a set of coordinate points, B sub 1 to B sub 2m plus 1, right? Because that are the number of elements we have within that window. And correspondingly, we would define each one of them with a m comma n coordinate point. Okay. Okay. So if I were to look at a row window, right, which has of size 2m plus 1, basically I could define all its coordinates by 0 comma n, where n goes from minus m to m. Okay. I can do the same thing for a column. I can define its coordinates as m comma 0, where m goes from minus m to m. Okay. So a simple example of a column 3 window would be minus 1 0 0 0 and 1 0. Okay. Yeah, makes sense? Okay. Okay. Similarly, I can define two-dimensional windows. You have a square, a cross of different size. Okay. Now, the other thing is when you define two-dimensional windows, okay, especially a cross, right, which basically looks like that, I can actually define the cross as a union of two one-dimensional windows. Okay. So a row union with a column would give me the same result. So what that also means is that I can actually perform a cross operation, windowed operation on my image by actually doing a two-step process. I can run a row operation on my entire window first and then a column operation. Okay. And from a speed perspective, that has significant benefits as opposed to running two-dimensional windows. Yes.
How about the cycle?
I'm sorry?
Cycle. The definition of cross. So how about the cycle?
A circle?
Yes.
Yes. So you can also create a definition for a circle, but circle inherently is a two-dimensional structure, right? So I can't simplify it and break it into a union of multiple one-dimensional structures, right? So operations like square and so on and so forth, those are a little difficult to do with unionized one-dimensional operations. All right. So given all of that, essentially if I had to perform a windowed operation, first I need to create a windowed set. Okay. A windowed set is nothing but a limited number of pixel values that I'm going to include on which I can perform a particular binary operation or any logical operation for that matter. Okay. So to define a windowed set given by window B over an image I, right, we will write that as being B dot I of I comma j, which is basically the set of pixel values, intensity values given by the image I over the position I comma j and the coordinates shifted according to the coordinates of window B, right? So I would have basically I of I minus m j minus n, where mn belongs to B, right? So any windowed operation that I would mathematically describe would be given by this. Basically this gives you a set of coordinate points for which you're going to use the pixel values to perform a particular operation. Right? So if I define B to be row 3, then B dot I would be given by I of ij minus 1, ij, and I of j plus 1, right? Because the coordinates for row 3 is 0 minus 1, 0 0 0 1, right? Make sense? Yeah. Similarly, I can define the set of coordinates for any particular window that I wish to use over a particular image. Okay. All right. Now once I've created my windowed set, I can perform any operation on that, right? An operation, let's say that I define by a function g, right, over the windowed set, which will give me a new image j. Okay. Now j in general would be a filtered image, right? It's an output because of performing operation g over the image given or windowed set of the window and the image. All right, which brings us now to the fact that we have to deal with these empty regions, right? Because if I have to start processing using these structuring elements, and if I wish to process the first pixel in my image portion of my window is going to sit outside the boundary of the image. So what do I do with the boundary of the image? Okay. So the general rule of thumb for dealing with that is replication, which means for every pixel that sits outside of the image, right, defined by a windowed set, you replicate its value to the closest pixel of the image. Okay. So the value here would be the same as this, same as this, same as this, and so on. Okay. All right. So this is the typical rule of thumb that is used for processing images. Now, we will go into a theoretical basis of that a little later, right? But a lot of times, in terms of conventions, okay, this is by far the most common. The other convention you will find being used sometimes is that you simply ignore a 1 pixel boundary around your image, right? So you actually start processing by 1 pixel inside. Now that works very well if your window is no larger than a 3 by 3, okay? Right? If your window is a 5 by 5, well, you need to skip 2 pixel boundaries around your image. If it's a 7 by 7, more and more, right? So if your window gets larger and larger, you have to skip many pixels in the boundary of the image. Okay? So that's a trade-off. But there's a trade-off in this convention as well, which is as your window gets larger, you have to pad more and more of these pixels. You have to replicate more and more as well. Okay. Okay. So, in terms of actual processing, right? We were talking about basic things that we want to do as morphological operations on our images. We wanted to increase the size of the object. We want to dilate it, right? We wanted to shrink it, which is erosion, and potentially actually fill holes, gaps, peninsulas, and so on and so forth. So the first operation we'll define is a dilation operation, and in fact the dilation operation turns out to be nothing but a OR operation over the windowed set. Okay, so if I take all the values in my windowed set and simply perform an OR, right, and take the end product of the OR operation and replace the I comma j value of my image with the resultant of the OR operation, and that helps me construct a new image. It turns out that the new image will be a dilated image of your original image. Okay. The other thing is erosion. If I wanted to shrink an object, well, simple. I would do an AND operation over the windowed set, and that would give me a eroded image. Right? The region would actually shrink in size. Median, right? A median is basically a binary majority operation. Okay? Now it has very nice properties in terms of how it affects the shape of the regions in a binary image. That being, it tries to minimize the effect on shapes. Okay? So if I were to perform a median operation over my windowed set, which is a majority operation in the binary case, over my windowed set, what I would get as a result is I would actually be able to eliminate very, very small objects as well as eliminate very small holes. But in general, it would not affect the shape of the object. Okay? It would not shrink it or it would not make it larger. Right? So if you remember our example of blob coloring, right, where we created the largest blob but we had holes in it, right, and we solved that problem by taking the knot and doing a blob coloring again, which you can imagine is not a fastest operation. It's a time-consuming operation, processor intensive. I can actually do a median in order to fill those holes, and I would be able to get rid of those holes. Okay. So this is what a dilation operation would look like. So imagine that you have an image portion of it. This is a region, right, and this structuring element highlighted in light blue is my structuring element, right? Keep in mind that what's over this is also light blue, right? So the entire thing is my structuring element. If I were to process this image with a OR operation over the windowed set, as I go across, the end result would be this. I would be able to increase the size of my object to what's in the light blue region, okay, and you would see the same increase over here, and this would be the structuring element that I'm working with. Okay, so simple 3 cross. Make sense? So what you would have done is basically increase the size of the regions that are present. Yeah.
Shouldn't the center of that structuring element be on the pixel?
Right. So basically the way it would work, you would start off basically right here. This is how your right. You would start right there. Okay. You would perform an OR for all the pixels here, right? All the pixels here are 0. So you get a 0, nothing happens, right? You move across, right? And the first time you're going to affect something is when basically you come here, right? So now my window is sitting here, right? Looks like that. I perform an OR operation, right? I have a bunch of zeros and a 1. The result of that is going to be a 1, right? So now this pixel is going to be colored 1. So as a result, all I've done is increase the size of this object. So this thing looks blue now, right? And I keep doing this across the entire image, and your end product is going to look like this. Right? So you dilated the object. Does that make sense?
The way I'm perceiving it as being put in the structuring element in the pixel.
That's right. That's what we are doing, right? Right. So this is, so the coordinates, this is I comma j, right? This is I j comma 1, I of j plus 1. This is I minus 1 j. This is I plus 1 j, right? So those are my coordinates for the window, right? The pixel values within that are all, right? So now I'm performing an OR on basically 5 pixels, right, which is all zeros. Right? I get a 0, right, which becomes the value for j I comma j equals that, right? So my new image, which I'm going to get, is going to have a value of 0 at this location. Now this window is going to shift 1. Now this becomes I comma j. I perform the same thing over again, and I get a new value for j of I comma j. Okay. When I'm done raster scanning this entire image, I get a full j of, basically full image j, right, where each I comma j has a new value now. Okay. Yes. If b is square, yes. So, well, okay. All right. So let's say if b is a square window, okay. So let's define it to be right. That's a square window. Right. So if this is a square window, right, basically you will have this value, which will also become a 1, right? So this would also become full. Similarly, when you move out, this is going to be full as well. So the way your shape changes is going to be dependent on the kind of window you have used. Okay? But broadly speaking, the end result is still a dilation. You've increased the size of the object. Okay? Yeah. Everyone okay with all this, right? Okay. So if you were to try to think of the global effect of a dilation operation, the easiest way to conceptualize this is if you take a black region, think of a rolling ball basically that sits at the boundary of your black region, right? Except the rolling ball sits on the white side of, so it sits on the background side of the object, right? And the ball rolls around, and wherever the ball covers the region, that's the increase in the size of the object. Okay, so basically I would take this ball, roll it around, everything that you see that's outlined as a red boundary would now become the new shape or new size of that of the region. You would get a result that looks like that. Okay, make sense? All right. Now, the opposite of that is an erosion operation, right? What that does is basically reduces the size of the region that you have. So if I were to take the same structuring element, run it on an image that looks like this, the object would be gone. Okay? Both of these would be eliminated. Okay? That would be the result of an erosion. It's shrinking the image. Okay? Now in terms of a global effect, it's the exact opposite. So now think of the regions that you have. Think of a white ball, right, that's placed inside and roll it around, and that's the kind of shrinking that you would get as an end result, right? So it shrinks the region that you have, it widens the holes that you have. Okay? Opposite effect. So in general, if you want to think of qualitative values or qualitative aspects of these operations, dilation will always remove object holes that are very small in size, right? Because the holes get filled, objects get larger. So dilation also will remove these kind of gaps that you have, okay? Because if the gaps are narrow, they will get filled as your object increases in size. So you would get objects that look like that. Dilation in general can be thought of as a complementary operation to erosion, right? So I can take an object, dilate it, I would get that. I can take the knot of it, erode it, and I would get that, and take the knot of it, I'll come back to this. Okay? Erosion, on the other hand, will basically remove objects that are very, very small in size. Okay? And at the same time, it will also remove any peninsulas. So anything that's sticking out of the object will also get eroded. If it's minor, we'll get rid of it. Okay? So it's a shrinking effect. Again, erosion can be thought of as a dual operation to dilation. So you can knot everything, perform dilation, knot again, and you'd get back to the result of an erosion operation. Oh, sorry. All right. Now, keep in mind that these are erosion and dilation are dual operations with respect to complementation, but they are not identical. Okay. So you can't actually perform an erosion on an image and perform dilation and expect to get back to the original image. Okay. The reason for that is when you do erosion, you get rid of objects. Doesn't matter how much dilation you do, you're not going to recover those objects. Right? Once objects are gone, they're gone. When peninsulas are gone, they're gone. You can't grow them back. So you can't use these kind of operations in that fashion. Median, right? There is our majority operation in the binary case, and the median has nice properties. So if you think of applying median with this structural element on an image like that, what would you expect to get? Single pixel objects, single pixel holes are gone, right? But other than that, the regions that are present in the image remain as they are. Okay? No major shape change in terms of erosion. No dilation, no erosion of the basic shape. So median, in fact, can be thought of as a smoothing operation. Right? So what you've done is actually smooth the region rather than changing the shape of the region. Right? Make sense? So majority operation or median in terms of processing, right? Certainly in the case of binary images, and we'll see also in the case of gray level images, is a very effective smoothing operation. It's a filter. So what are the qualitative properties of median? One, it will actually remove both objects and holes of very small size, as well as it will get rid of gaps and peninsulas which are very narrow in width. Okay? So if you were to take a median of an image like this, it will get rid of very small objects, very small holes. Median with gaps and peninsulas, get rid of the gap and the peninsula. Keep in mind the degree by which this actually works is dependent on the structuring element. Right? Larger the structuring element, larger these kind of effects will be. Larger the holes that will be filled up, larger the peninsulas that will get eliminated. Smaller the structuring element, smaller the effects. Okay? Now, median is actually its own dual, right? So I can apply the median on the knot of an image, or I can take the median of an image and knot it, they would be the same. Okay. Right? Okay. Now, given that the basic operations we have defined in terms of morphological processing are dilation, erosion, and median operations, right? Dilation and erosion actually affect the shape of the object, right? They help us either fill holes, remove peninsulas, so on and so forth, right? But they don't necessarily act as simple smoothing functions, right? They don't necessarily give us the effect that we would desire in terms of trying to smooth out the shape without necessarily increasing or shrinking the object. So in order to create smoothing filters similar to median, we can do a combination of dilations and erosions. Okay? Because remember, dilation and erosion in general has very complementary effects to each other. Right? Right? Make sense? So basic smoothing operations that we wish to perform on images, binary images, can be defined by a combination of dilations and erosions. Two basic things that you will tend to use quite a bit are open and close operations. Open being defined as first eroding the image with a structuring element and then dilating the image with a structuring element. Close, on the other end, is being defined as first dilating and then eroding the image. Okay? All operations are to be read inside out. Okay? Now, when we do these kind of operations, these have properties that is very similar to a median operation. Okay? So, if they are very similar to a median operation, why define them? Why not just use a median? What happened? Are we running too late today? What time do you have? 2:20. 2:20. Is that why everyone's quiet? Come on. Any thoughts? If median has properties that are similar to an open and close, why should we define open close operations? Why not just use median because it's equivalent or at least gives us similar effects, right? More effective in what way?
And then it does some of the properties of the median, but
Not all.
not all.
There are some that may be better than median. Yes, I mean that's possible, and we'll see exactly what are the properties, right? None of these are perfect. I mean, none of these operations have a property which says, here's my application and this is the perfect property for this application. They're mix and match, right? So we have to find the optimal use of these operations. But most importantly, the reason we wish to define smoothing operations using open and close or a combination of dilate and erodes is because they are fundamental logical operations as opposed to a majority operation, right? Using and or versus doing a majority is very different in terms of processing time. and an OR is going to be significantly faster than computing a majority over a windowed set at any given day, right? Yes?
The only reason is the less computing.
Well, no. So yes, less computing is a major reason. Qualitatively, they have similar properties, not identical. Okay? And we'll see what the properties are. But I guess, well, I'm kind of out of time. So how about I stop here and we'll pick it up again with open and close next time. Okay. Now, I think the unfortunate part is your video stops at this slide as well. So unfortunately, you don't have the video for the slides beyond this, because that's what I was going to cover beyond today. So I'll cover the remaining of the slides on Monday, or sorry, on Wednesday. And then Wednesday, if you guys have laptops that you're going to use for doing your coding, your exercises with your open CV environments and so on and so forth, bring them, okay? Because on Wednesday, we'll run a small exercise in OpenCV. We'll write a piece of code, we can run, see what the effect is, so on and so forth. Okay?
When we talked about thresholding, we saw that the result of thresholding depended on what is the threshold parameter that we are taking, and we had ways of determining that thing.
Mm-hmm.
And similarly, for these morphological operations, we see that the result would depend on the structuring element that we take.
That's right.
So is there any way, just like for thresholding, that a way for determining the structuring element?
Well, so different structuring elements have different effects. There is a generalization as to the kind of effects you have because of the dimension of the structuring element, and we'll talk about that. But there is no predetermined way of saying that this is the optimal structuring element for my application. Just like there is really no one way that I can tell you that you can find this threshold and that will be the optimal threshold for your application.
So it's almost the same heuristics pattern.
Well, so they're not necessarily heuristics, but you can think of all of these as processing steps which you have to put together in order to sort of extract context of your image. And keep in mind, I mean, we don't necessarily, we try to optimize the result that we can obtain in a pipeline of processing steps, but we are not dependent solely on the output of one, in the sense that if I could solve my entire image processing problem by figuring out a perfect thresholding routine, right? Yes, I would put all my energy in that, right? But given the fact that there are too many variabilities that I cannot control, right? For example, lighting may change. The kind of images that I get may change. The objects and the background may change. Now, what you can do is, there are two ways of solving this problem, right? And one has to work through whichever is the better solution. If you have full control over your imaging environment, by all means, try to work on your imaging environment. Try to get it as constrained as possible. Try to narrow the number of variabilities that you deal with in terms of processing, certainly. But if you don't have that, your other option is to work with the variabilities that you have and design the best algorithms that you can in order to account for all the variabilities. Right? And in general, there are not too many cases where we have full control of the imaging environment. Right? So as a result, we have to work with variabilities, and we have to account for those variabilities in terms of creating processing algorithms that are capable of dealing with inaccurate segmentation, inaccurate thresholding, inaccurate blob coloring, inaccurate median operations, smoothing operations, and so on and so forth. That's it. So, and you will get a nice exercise to explore those things, right? So that's why. So if you're going to use laptops, or just at least bring whatever you're going to use if you can. If it's laptop, of course, if you're going to use a desktop computer upstairs, you can't bring that along. but you know, you can share with your neighbor if they have one. So we can at least run through an exercise. The code that we write in class, of course, will be posted, so you can compile it later and see for yourself how that might work. Okay? And then as we get through binary processing, we'll start talking about point operations and grayscale images. And hopefully by the end of next week, you will get your first assignment to start working on. Okay? All right, very good. I'll see you on Wednesday.